Hale, today we are going to move on from talking about one variable data, and we are going to start talking about uh, bivariate data. So two groups of quantitative data that we want to see if there's a relationship between. And hopefully this is something that you have some experience with. When we're comparing two groups of quantitative data, we create scatter plots. And so let's talk about the pieces of this scatter plot. Here we have data for groups of deer and the percent of the region that they were observed in, the percent that was woodland. And so each data point represents one group of deer. And the first value would be the percent of that region that was woodland. And then the second value would be the size of that group of deer. And so you would know these traditionally as X and Y. And so each data point, the X and the Y, the percent of woodland, the size, they specifically go together. So when we're creating these scatter plots, we need to be careful that our data in our one quantitative group corresponds to the appropriate other quantitative group. So here we have 12 data points, all telling us about 12 different groups of deer and the size of that group and the percent of the region that they're in that was woodland. This x-axis, the horizontal axis, x is what we would traditionally call it. We would call an independent variable. We might also call it an explanatory variable. Our vertical axis, typically a y value, but now we will call it a dependent. Alternatively, we could call it a response. We are trying to see in this scenario if there is some relationship between the percent of woodlands in a region and the size of a group of deer that we might observe. And so one thing we would want to do once we collected this data and we have displayed it in this way is we would want to talk about what it looks like, much like we described histograms and we described distributions of one variable. We can describe what our scatter plot, what our relationship between these two quantitative variables will look like. And we will talk about its shape. We will talk about its form. And we will talk about its direction. So our shape we will describe typically as linear or curved in some way. Our form we are going to talk about as sort of a level of strength. So sometimes we'll say weak, moderate, or strong. And then our direction is it positive, which goes up to the right, or negative, which goes down to the right. And so I would say here that this scatter plot, if we were to sort of draw not a line that goes through all the dots, but that hits most of the points, we would say that this is curved. Your strength has to do with how tightly packed the data points are if we were sort of following the path that they were on. And so these are all pretty tightly packed. And so we would say there's a strong relationship here. And we are going down to the right, so it is negative. And of course, much like we were describing a one variable data set when we were describing a histogram, we would make sure we'd always want to describe that within context of what this was displaying, and complete sentences, and all of those things. Here we're looking at a data set that has to do with this, I believe, the size of homes and the price of those homes in thousands. And if we were to sort of draw a line through this data that would be close to most of the data points, this looks like it is linear. Our data points aren't super tightly grouped together, but they're also not scattered so far apart. So we might say this has a moderate strength. And we are going up to the right, so it is positive. And one thing that we could get that we had in our one variable data sets is there is a potential for an outlier. And an outlier is a point, I'm going to make one up here. An outlier is a point that would be far above or below. And of course, we should speak in terms of potential outliers here. An outlier is something that is far above or below the rest of the data points. And we're going to speak with some more specific language when we get into the next couple of lessons when we talk about linear regression. But an outlier is a point that is far above or below the rest of the data. So when I look at a point like this point, it isn't with the data set. It's kind of out there all by itself. However, if I'm looking at the path of the rest of my data, it's not really far above or below any sort of line that I could draw through them, or far above or below the path that it's taking, this positive path up to the right. And so we wouldn't consider that an outlier. We could give that a different name that we'll talk about in the future. Oops. And so I just wanted to show one more. Here we have the percent of trees harvested and squirrels per plot. Again, just looking at sort of how this is shaped. I would say that this is pretty linear. I would say this is strong. And it's negative. And we need to be careful that when we talk about positive or negative, that doesn't mean good or bad. It just means what is the path of our data points? Are they going up to the right, or are they going down to the right? So what's happening here is typically as our percent of trees harvested increases, our squirrels decrease. Over here, as the size of our homes increased in square feet, the price of those homes also increased. And that so gives us an idea of the pattern when we describe it as positive or negative. When we look at those two types of quantitative data sets and we plot them in a scatter plot, we can talk about its relationship, the association that's involved. But what we really want to get into is the correlation. And correlation is different than a relationship because it's specific to when we have a linear relationship. Correlation coefficient we give R, so we give a value to the correlation between two quantitative data sets. We label with R. And we're allowed to calculate R if we meet a few conditions. When we create our scatter plot, we need our data to be linear. We need to have no outliers or no points that would make you feel like that's a potential outlier. And of course, in order to calculate correlation, our data has to be quantitative. So this has to do with quantitative data and not categorical. And so what I'd like you to do is, and I've already done it here, is I'd like you to go to your stat lists and put a list here. We are comparing recreational drug use in several countries in Europe and the United States, 10 to be exact. And we are trying to see if there's a relationship between marijuana use and other recreational drug use. So go ahead and put these in. It's important to put them in the correct order because we need to have data points that represent each country. So we'll have a data point for each of the 10 countries. And if we don't put them in correctly, we are going to be mixing and matching the data points. So pause here, put those in, and then we'll create a scatter plot. So hopefully you have them in, and we can do second y equals. I'll choose my second plot because it's on, and I'm going to go ahead and I'm going to choose that first option. And so it's going to give me an X list and a Y list. The X list, that's your independent explanatory variable. The Y list, that is your dependent or your response variable. We're trying to see if marijuana use affects other drug use. And so our X list, our independent variable, is going to be L1, our marijuana use, and then our Y list is going to be the other drugs. And so we can zoom 9 once we have that. Oops. And we can graph our scatter plot. And so it looks to me there like that's a linear path. Pretty linear. It doesn't look like there's any points that are out all the way on their own above or below the rest of them. So no potential outliers. And of course, these are quantitative data sets, so we can calculate our correlation coefficient. So before we go ahead and calculate R, we need to hit mode, and we need to arrow down to where it says stat diagnostics. And we want to arrow over to on and hit enter and make sure they're on. And this way, when we do our calculations, we are going to get all the values we need. We'll talk about R today, and we'll talk about the remaining values in a future lesson. So we're going to hit stat, and we're going to calculate. We do have two variables here, but we're not going to do two var stats. We're going to go down to option 8. That's linear regression, which we'll talk more about in the next couple lessons. We want to choose number 8. We're going to tell it our X list is list 1, our Y list is list 2, and then we're going to calculate. It's going to give us 4 different values. The value we're looking for is R, correlation coefficient. R is always going to be a value between -1 and +1. +1 is a perfect linear relationship that goes up to the right. -1 is a perfect linear relationship that goes down to the right. R value of 0 means there's absolutely no correlation between the two variables, and a scatter plot with a R value of 0 would look totally random, no pattern at all. The closer we get to positive or -1, the stronger our relationship. The closer we get to 0, the weaker our relationship. Somewhere around a 0.5, that's pretty moderate. There is some relationship, but it's not very strong. We looked at our scatter plot. It went up to the right. It was linear. You can see by our correlation coefficient that it's positive. So we have a positive relationship between marijuana use and other drug use. It's linear, meaning as marijuana use increases, the other drug use also increases. And the correlation coefficient is 0.9341. That gives a value to the strength. It's very strong. It's close to 1. It's a very strong relationship that we have between marijuana use and other drug use based on our data set. It would be a bad idea to take this information and try to make some sort of inference or conclusion about the entire world. We could say, based on our data set, there seems to be this strong positive linear relationship between marijuana use and other drug use in these countries. What we do need to be careful of is making the mistake of confusing correlation and causation. Correlation does not equal causation. Just because we have a data set that shows a strong relationship doesn't mean that we have a cause and effect here. The only way to prove cause and effect is by doing an experiment, and doing an experiment getting people to use drugs would be unethical. And so we can say, based on our data, there is a strong relationship, there's strong correlation, but we should not say that marijuana use causes use of other drugs. And one of the reasons there is we have these things that we call lurking variables, and those are other conditions or other characteristics that would be related to both of our variables that might cause them to look like they are related. For instance, real quick, if we were comparing AC sales, air conditioner sales, and ice cream sales, we might see that as air conditioning sales increased, ice cream sales also increase. It would be silly to say that selling air conditioners causes ice cream sales to go up. There would be a strong relationship, but there would be a lurking variable there, something that's related to both of those things that's causing them both to go up at the same time. And you probably might have guessed that it's the temperature. As the temperature increases, we're going to need our air conditioners replaced, and we are probably more likely to stop and get an ice cream because it's hot out and we want something cold. So I have one for you to try. Put this data into your calculator, create a scatter plot, describe it. If possible, well, we'll practice calculating the correlation coefficient no matter what. You could make a note on whether or not that was appropriate or not based on is the data linear and are there any potential outliers? If you need help with the calculator or if you need help with any of these ideas, please do ask. Take your time on this one. We'll talk about it together, and good luck.